Okay, so in this video, what I'd like to do is look at the ALEX objectives for this week, which cover the material in section 7.1, 7.2, and 7.3 of the text. And we continue to look at some periodic trends, and in particular, how position in the periodic table is related to the number of valence electrons and the type of bonding that atoms do. And then we look at it's kind of a review topic. We look at the basics of constructing what we call Lewis structures. So there are 15 ALEX objectives this week, and I'm going to work through an example of each of them. So let's see what we've got here. So the first thing that we're asked to look at is to predict the relative electronegativity of some neutral atoms. So something that I wanted to point out to you is in the ALEX periodic table, when you click on an element, you get some more information about it. And one of the things that it gives you is the electronegativity. So I'm going to place these in order using the trend for electronegativity, but I then want you to be aware that it would be extremely wise to then check that you actually do have them in the correct order by clicking on each element and seeing what its actual electronegativity is. So electronegativity increases towards the right of the periodic table and towards the top, and we know that fluorine has the highest electronegativity. So basically like that. Now electronegativity is a measure of how atoms pull electrons towards themselves when they are bonding with other atoms. So we know that the noble gases tend not to bond with other atoms, so we're not really going to be considering the noble gases as part of this trend. So that being said, let's what we've got. We've got chlorine, iodine, and tellurium. So chlorine, iodine, and tellurium. And we're asked to list them in order of decreasing electronegativity. So the one that is furthest to the left and lowest down would be tellurium. That would be less than iodine, which would be less than chlorine. So that would be my first group of 3. And now I've got nitrogen, carbon, and oxygen. So I'm just going across. Hopefully you can see this. I'm just going across period 2 there. All right, just across period 2 there. So decreasing electronegativity would be oxygen would be less than nitrogen, would be carbon would be less than nitrogen, which would be less than oxygen. So then I would go in and click on each of those 3 values and make sure that I actually have everything correct, especially if it was a test. Okay, so this question you want to be a little bit careful about. It says predicting a bond polarity. So how we predict bond polarity is we look at the electronegativity of each element, and then we know that electrons that are in that bond will be pulled towards the more electronegative element, and that end of the bond will be a little bit negative relative to the other end of the bond. So really what we need to do, and I've just pulled this out of the book, figure 7.6, and it just saves me clicking on all of those elements every time, is I just have to look at my pair of atoms and decide what's going on. So it says in each of the molecules drawn below, one chemical bond is colored red. Decide whether this bond is likely to be polar or not. And so our cutoff for polar is a difference in electronegativity of about 0.4. But in this example, that when you see that, the consequences of your bond being polar will affect the compound's properties. So but if there is any difference in electronegativity, that bond will be polar to some extent. So let's have a look here. We've got carbon and oxygen. So we have 2 different atoms. Difference in electronegativity here of 1, and oxygen is more electronegative than carbon. So the highlighted bond is polar, and oxygen is the more polar or more negative element. Okay, so we've got bromine and fluorine. Well, they're going to have different electronegativities. Fluorine is very electronegative relative to bromine. See, there's fluorine, there's bromine, difference in electronegativity 1.2. So that will definitely be polar, and fluorine is always the more negative atom in a bond. Now, in this case, we have two identical atoms in the bond. Both of them are going to have the same electronegativity. For carbon, I believe it's 2.5. So what that means is that this bond is non-polar, right? Non-polar. Two identical atoms in a bond will always give you a non-polar bond. Okay, I think this week it's a bit threatening to see that we have 15 topics, but a lot of them are quite easy, quite quick to get through. Okay, predicting relative bond polarity. So this is important because the bigger the difference in electronegativity between our two atoms, the more polar. So that's all we're really talking about. In here, we have to list these bonds in decreasing order of polarity. So you always want to be careful with ranking problems. So we want to go from most polar to least polar. And we're going to pick them in order of, so that's going to be 1, 2, 3, like that, right? Okay. Now, what's interesting, in each of these bonds, one of the atoms is the same. It's hydrogen with an electronegativity of 2.1, and then we've got 3 halogens. And so what we know is as we go up a group, we get increasing electronegativity, right? So when I think about this, the one with the lowest electronegativity is going to be iodine, 2.5. And then we've got bromine, and then we've got fluorine. So when we think about the differences in electronegativity, we can see that it's going to increase because the hydrogen is fixed as we go up. So the most polar here is going to be the fluorine. Then the second most polar will be the bromine. And then finally, we've got the iodine. It's a decreasing order of polarity. And if you want, you can calculate delta En in each case, right? And you can see for the hydrogen fluoride, for example, it will be 4 minus 2.1, which is 1.9. And then if we did that for, say, the iodine, it would be 2.5 minus 2.1, all right? And you can see that it is only 0.4, so it's barely polar, all right? So if you need to, calculate it if you can't convince yourself that you've got it right. Okay, so this is what predicting the relative ionic character of a chemical bond. So what's important here is to recognize that bonds range from pure covalent, where we have perfectly equal sharing of electrons, through what we call polar covalent, where we have unequal sharing of electrons, to when we no longer have sharing at all of electrons, we have what we call ionic bonding. And in ionic bonding, we don't have electrons being shared between two atoms. Electrons get transferred from a less electronegative element to a more electronegative element, right? So pure covalent bonding would be something like where we have two atoms with identical electronegativity, and then the electrons being shared are going to be sitting halfway between each atom. Polar covalent is when we have atoms with different electronegativities, and the electrons that are being shared lie closer to the more electronegative atom. And then ionic bonding is where we have complete transfer of electrons from one atom to another, normally from a metal to a non-metal, and then the bond forms as a result of the attraction between the formed ions. So what we're really looking for here is to see, and this is a scale, right? So you can have, it doesn't have to be complete transfer, so we're going to, what we're really doing is looking at, when we're ranking these in percent ionic character, is we're ranking them in order of increasing delta En. So what we are meant to do is decreasing order of ionic character. So, sorry, it shouldn't be, so then it should be decreasing difference in electronegativity, right? So if we had really big difference in electronegativity, it would be ionic, right? And if we had smaller difference in electronegativity, or no difference in electronegativity, it would be pure covalent. So something I can see here is that these guys here, metal with a non-metal, that's going to be ionic, isn't it? Right? And then this guy here, where we've got two atoms of the same type, that's going to be pure covalent. And then in here, where I've got a semi-metal or a metalloid with fluorine, that's most likely going to be polar covalent. So the question is, though, how would I distinguish something like sodium fluoride from strontium fluoride as far as percent ionic character? So that's why the electronegativities are important to get this. So let's have a look here. I know that this is not going to be ionic at all, so I'm going to put that as 4. And then I'd be this is polar covalent, so it's not ionic at all. So that's but it's not pure covalent. So that's going to be number 3. And then my difficult one is going to be ranking sodium fluoride and strontium fluoride. Now these guys, I'm pretty convinced they're going to be 100% ionic character. All right, 100% ionic character. But let's calculate the difference in electronegativity. Sodium is 0.9 and fluorine is 4, so 4 minus 0.9 gives me 3.1 for the difference in electronegativity there. And then we've got strontium is 1, so 4 minus 1, that's going to give me 3. Wow, well that's well above our cutoff for percent ionic character. So how might I do this? I would go 1, 1, 2, 3, because once you get complete transfer, it's 100% ionic. So I don't think there's any difference in the percent ionic character between sodium fluoride and strontium fluoride. It is. So if you remember, once you get bigger than like 1.7, you've got 100% ionic bonding. So there's a table in your book that talks about these things. So let's see if we can find it exactly where it is. Here we go. So they have the cutoff at 1.8. So, different people disagree about that, but 1.8. So once you get above 1.8, it's 100% ionic and it's indistinguishable. Here we go. All right. So you might want to have that little table handy. All right, let's have a look at this one. Drawing the Lewis dot diagram of a main group atom or common atomic ion. So main group just is the same as representative element. It means one of those groups that in the North American numbering system has an A in the group number. And so the Lewis dot diagrams for the elements or for the main group elements is pretty simple. If it's in group 1A, it gets 1 dot. If it's in group 2A, it gets 2 dots. If it's in group 3A, it gets 3 dots, all the way up to 8A. And then the dots kind of go like this. You put 1, you put 2, you put 3, you put 4, and then once you've got 1 at each of the 4 compass points, then you begin doubling up. Now, it doesn't matter the order that you put the first dots, whether you go like north, south, east, west first, it doesn't matter. It doesn't matter whether you go around clockwise or anti-clockwise. That's kind of irrelevant. The important thing is that you get 1 dot at each of the 4 points before you double up, and then you never more than double up, right? So that's that. So to create a cation, you remove electrons. To create an anion, you add electrons. So here's calcium. Here's the neutral atom of calcium. It's got 2 dots. And then we're going to go to calcium plus, and we're going to do that by removing 1 electron. So that means we've got to take 1 dot away. So there's our Lewis dot diagram for the calcium plus cation. Pretty straightforward, right? Okay, below is the Lewis structure of the ammonia molecule. Okay, count the number of bonding pairs and the number of lone pairs around the top hydrogen. Okay, so bonding pairs are those that exist between atoms, right? So in this molecule, they're the ones that are between the nitrogen and the hydrogen. And then lone pairs are the ones that are, let's pick a different color, not shared at all. They're just associated with a particular atom. Now, in our case, we want to look at that guy there, that top hydrogen. And what I see is that there are 0 lone pairs. In fact, hydrogen never has any lone pairs around it. But there are these 2 electrons in here that are being shared. So there is 1 bonding pair. Sometimes people get confused. You have to be on the lookout for that word pair, because it could equally as easily as ask you how many bonding electrons are there, but it didn't. It said how many bonding pairs. So you've got to read the language. Pay attention to the language. Okay, this looks similar. Below is the Lewis structure of the bicarbonate ion. Count the number of bonding pairs and the number of lone pairs around the carbon atom in this molecule. So there's the carbon, and looking at this already, I don't see any lone pairs. All I see are bonding pairs. And how many are there? There is 1, 2, 3, 4. So 4 bonding and 0 lone pairs. Here we go. 4 bonding and 0 lone pairs. Not too bad. Just got to be careful, right? Just got to not miscount. So this question, next one is counting valence electrons in a molecule or polyatomic ion. So the first thing that I like to do is to see if I've got a molecule or a polyatomic ion, and HNO3 is a molecule. So that makes it easy because I don't have to add or remove electrons to account for the charge. So the number of valence electrons in this molecule is just going to be the number of valence electrons that's in 1 hydrogen, 1 nitrogen, and 3 oxygens. Now, those atoms, hydrogen, nitrogen, and oxygen, are all representative elements. And for representative elements, the number of valence electrons is just equal to the group number, when it's given in the North American numbering scheme. So I'm just going to refer to my handy dandy little diagram here. So I've got one hydrogen, and he's going to contribute one valence electron because he's in group 1A. I've got one nitrogen, and he's going to contribute 5 valence electrons because he's in group 5A. And then I've got 3 oxygens, and they're going to contribute 3 times 6 because they are in group 6A. So how many have I got? 1 plus 5 is 6, plus 3 times 16 is 18. So 6 plus 18, 24 electrons. Don't be ashamed to use your calculator. You want to make certain that you get it right on your quiz or test. Deciding whether a Lewis structure satisfies the octet rule. Okay, so there are a couple of requirements here. Requirement number 1, that your molecule / ion has correct number of valence electrons. If it doesn't have the correct number of valence electrons, there's no point in going any further. The second thing is that each non-hydrogen atom should have an octet, and then hydrogen should have a duet. Okay, so that's what is going on here. That's where we're at, all right? Okay, so let's have a look at this. We've got to read it very carefully. Decide whether the proposed Lewis structures are reasonable. So here's our molecule, HCN. So first of all, I want to count up how many valence electrons should it have. So we should get 1 for the hydrogen, should get 4 for the carbon, and we should get 5 for the nitrogen. So that it should have a total of 10 valence electrons. How am I getting those numbers? Hydrogen's in group 1A, carbon's in group 4A, and nitrogen is in group 5A. So does it have 10 valence electrons? 2, 4, 6, 8, 10. It does. So it passes our first check. The next thing is, does every atom except hydrogen have an octet? 2, 4, 6, 8. So the carbon, it looks good. The carbon looks good. But what about the nitrogen? 2, 4, 6. Nope, the nitrogen is no good. Right, the nitrogen is no good. What about the hydrogen? It should have 2, 2, it's good. So the problem is not that it doesn't have the correct number of valence electrons. It has the correct number of the valence electrons, but the nitrogen atom doesn't have the right number of electrons. It only has 6 electrons around it. It doesn't have an octet. Okay, so we got the first one done. So in this case, it wasn't a problem of the incorrect number of electrons. It was a problem of the valence count around the nitrogen being incorrect. Let's have a look at this. How many valence electrons should this guy have? It is CCl2O. So chlorine's in group 7A, so that's 7. Carbon's in group 4A, that's 4. Chlorine is in 7. Oxygen's in 6. So 7 plus 4 is 11, plus another 7 is 18, plus another 6 is 24. So this thing should have, if it's correct, 24 valence electrons. So let's add them up and see how many we got. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So it doesn't even get the correct count. Let's try it again. Let's just double check everything. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 24, or 20, 24, 22, 24, 26. So it looks like we got that correct, all right? Okay. We could do it one more time if we wanted to. Let's double check that we counted them up correctly to begin with. 7 plus 4 is 11, plus another 7 is 18, plus 6 is 24. So it has the wrong number of valence electrons. The correct number is 24. Okay. Let's go on to the next one. 3 oxygen atoms. So we got 6 plus 6 plus 6. So it should have 18 electrons in total. Let's see how many it has. 2, 4, 6, 8, 10, 12, 14, 16. Ooh, really? Let's do that again, just in case. 2, 4, 6, 8, 10, 12, 14, 16. So that Lewis diagram is out by 2 electrons. It has the wrong number of electrons. It should have had 18, right? Because we should get 6 for that guy, 6 for that guy, and 6 for that guy. So it's incorrect. So that's it, right? That's the problem. So it doesn't have the correct number, so we can just get, that's not the issue. All right. Now it's interesting, if you actually look here, every atom does have 8 electrons around it. It's just the wrong total number of electrons. Okay. Draw the Lewis structure for a hydrogen molecule. Well, I think we got lucky here because that's the simplest molecule that could ever be constructed. So it's a multi-step process for drawing a Lewis structure. The first one is count up your total number of valence electrons. So 2, and then hydrogen's in group 1a. So it's 2 times 1. So that's 2 electrons to work with. My next step is to identify my central atom. So is it hydrogen or hydrogen? Well, I think it will be hydrogen. And then I have to attach my outer atoms by a single bond. And there we go. And then you need to eliminate the electrons used to construct those bonds. So I have no electrons left. Then I complete my octets on my outer atoms. Well, this is my outer atom and he's already completed his octet. And then I have to place any leftover electrons on my central atom. There aren't any, so nothing to do there. And then finally, I would convert lone pairs to bonds if any of my atoms didn't have a complete octet. Well, there are no lone pairs and every atom has a complete octet, or in this case, duet, because it's hydrogen. So there is my Lewis structure for the H2 molecule. Pretty easy going, right? Hydrogen has 1 electron, hydrogen has 1 electron. These guys come together and they figure that it's better to share them and become stable with a noble gas-like configuration similar to helium, or identical to helium. All right. For each row in the table below, decide whether the pair of elements will form a molecular compound held together by covalent chemical bonds. So basically, molecular compounds form when you take a non-metal and you combine it with another non-metal. Could be even 2 non-metals of the same type. So really what we're looking for when we're trying to identify if it will form a molecular compound is, do we have 2 non-metals? And the nonmetals on the Alex periodic table are labeled in yellow. So do we have two yellow elements? So we got hydrogen and bromine. So yes, it will. And then we've got barium and carbon. So the answer is no, it won't. So that's no good. And then we've got carbon and chlorine. So we've got two yellows. So yes, it will form a molecular compound. So now we need to look at the Lewis dot symbol for each element. So hydrogen's in group 1A, it's got 1 dot, and bromine is in group 7A, it's got 7 dots around it. And what we're looking for is the number of octet vacancies. And that tells you how many covalent bonds that your atom is likely to form. So hydrogen wants to form 1 bond, bromine wants to form 1 bond. So what are these guys going to do? They're going to come together in a 1-to-1 ratio, and those unpaired dots are going to pair up like that. You see that? Let me make that one like that, and then that one like that. You see what's going to happen there? So the formula of the compound that we would predict would be formed by these guys would be HBr. Now, HBr, what are we going to call it? We're going to call it hydrogen bromide. There we go, hydrogen bromide. We have to remember our naming from Chemistry 161. And for compounds that begin with hydrogen that are not acids, we name them as though they were an ionic compound. We give the name of, we give hydrogen, and then we just give the name of the second element, and we change the ending to bromide. We don't need to include the prefixes mono if our compound begins with hydrogen. All right, what about this guy, carbon? Okay, so carbon, he's got 1, 2, 3, 4 valence electrons. They're all going to be unpaired. And then we're combining that with chlorine. Now, chlorine, she has, I don't know why I've decided that carbon's a boy and chlorine's a girl, but I have. She has, let's do this, 1, 2, 3, 4, 5, 6, 7. So we've got 1 unpaired dot around the chlorine. So what we're going to need to do to get this to work out is we're going to have 4 of these chlorines in total. Otherwise it's not going to work, is it? And each of them is going to have that 1 unpaired dot ready to join up with our carbon, right? And then when the compounds form, these unpaired dots are going to become shared electrons. So our compound would end up being carbon Cl4, okay? Cl4. So what's the name of this? According to the rules for naming covalent compounds, we give the name of the first element unaltered. The name of the second element, we change the ending to IDE, and then we add prefixes. We have a couple of rules for prefixes. If our compound starts with hydrogen, we don't need any prefixes. If our compound doesn't start with hydrogen, the only extra rule we've got is that we don't need to put mono if there's one of the first element. So this is going to become carbon tetrachloride. Okay, carbon tetrachloride is the name there. So it is CCl4 carbon tetrachloride. And the first one was hydrogen bromide. There we go. Now, yeah, it's not easy. So if I look at an oxygen atom, 1, 2, 3, 4, 5. Let's look at that oxygen atom again. If I look at an oxygen atom, 1, 2, 3, 4, 5, 6. You can see oxygen I would expect to make 2 bonds. Doesn't always, but it's what I would expect. If I look at a nitrogen atom, group 5A, 1, 2, 3, 4, 5, I would expect it to make 3 bonds. Doesn't always, but that's the typical bonding pattern. Carbon, 1, 2, 3, 4. I expect it to make 4 bonds. Fluorine, 1, 2, I'm rushing this a little. It has 7 valence electrons. I expect it to make 1 bond. So that concept of octet valencies can be really helpful. Predict the compound formed by 2 main group elements. So what are we going to remember is that metal and non-metal, they're going to give you an ionic compound. Whereas non-metal with a non-metal, it's going to give you a covalent or molecular compound. So that's what we're really looking for. Now, it does say in here, neither. So what are we going to get if we, if we decide neither? We'll have to cross that bridge when we get there. But the obvious thing would be if we're combining the only combo that we haven't considered would be a metal with a metal, and that's going to form something called an alloy, which isn't one of our options. So let's see what we've got here. Oh, of course, it's the first one, isn't it? The metals on the Alex periodic table are in blue. We've got lithium and magnesium. So that's actually going to be in the neither category, and we don't have to worry about writing a formula. The next one is where we've got a metal and a non-metal. We've got oxygen and cesium. Cesium is down here. Oxygen is over here. So we have metal with non-metal. So it's going to be an ionic compound. Now, how do we decide the formula? Remember that we've got to use our crossover rule if the ions don't have the same size charge, and we're just going to combine them 1 to 1 if they do. So cesium is in group 1A, so it loves to form +1 ions, and oxygen is in group 6A. It loves to form 2- ions. They don't have equal and opposite charges, so we're going to do crossover, and we need 2 cesiums for every 1 oxygen. So that's going to be CS2O. All right, what do we got next? Beryllium is a metal, and aluminum is also a metal. So 2 metals coming together forms neither an ionic compound or a molecular compound. So we get lucky there, and we don't need a chemical formula. So that was pretty good. Draw the Lewis structure for the phosphorus trichloride molecule. Now, the thing here is it says no octet rule exceptions. So we're not going to have any expanded valence shells, and we're also not going to have any electron deficient molecules. So don't worry if those terms don't mean anything to you, but that is an important thing to recognize. So phosphorus is in group 5A, and then chlorine is in group 7A. So count up valence electrons is your first step. So we get 5 for the phosphorus, and then 3 times 7 for my chlorine. So 5 plus 21, I've got 26 electrons to be dealing with. So that's the first step, is count up valence electrons. Now I have to identify what atom goes in the middle. Is it phosphorus or is it chlorine? And the one that goes in the middle, the easiest way that I remember it is the one with the lowest electronegativity. So decreasing En. And so phosphorus has a lower electronegativity than chlorine. So phosphorus goes in the middle, and then the chlorines are on the outside, and they have to be connected to the central atom by at least single bonds, or otherwise nothing is going to hold together. So to each of the single bonds requires me to use 2 electrons, and that leaves 20 electrons for everything else. So what I do now is I complete octets on my outer atoms. And in this case, I'm going to have to add 6 electrons as lone pairs to each of the chlorines. There we go. And so 3 lots of 6, I've got to take away 18 electrons, and that leaves 2 electrons remaining. So what do I do with those remaining electrons? Once I've completed octets on my outer atoms, if I have any electrons left over, I put them on my central atom as a lone pair, so they go in there. And then I have one final step to do. Now I have no electrons left. I've used up all 26 electrons. Let's just quickly count them. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. All I do now is check that my phosphorus has a complete octet. 2, 4, 6, 8. It does. So there is our Lewis structure for phosphorus trichloride. So with this problem, we have to recognize whether we are not following the octet rule and decide whether a Lewis structure is reasonable or not. There are 2 things that we're going to check. Number 1 is that the total electrons is correct. And then number 2 is that we have a octet for every non-hydrogen and that we have a duet for hydrogen. And if we don't have those things, it's not a good Lewis structure. So let's see what we've got going on here. So we've got carbon dioxide. This is the proposed Lewis structure. So for CO2, how many electrons do we need? We need 4 for the carbon, because carbon is in group 4A. And then we've got 2 oxygens, and they're each going to give us 6 electrons because they're in group 6A. So 4 plus 12, 16 electrons. So have we got it? Let's have a look. Let's count them up. 2, 4, 6, 8, 10, 12, 14, 16. I think it's good. 2, 4, 6, 8, 10, 12, 14, 16. So if there's anything wrong, it's not that we've got the wrong number of electrons, right? Now, does every atom have an octet? Let's see what we've got going on here. 2, 4, 6, 8. The oxygen on the left seems to have the correct number of electrons. Okay. What about the oxygen on the right? 2, 4, 6, 8. The oxygen on the right seems to have the correct number of electrons. What about the carbon in the middle? 2, 4, 6, 8. They all seem to have the correct number of electrons. So everything there has the correct number of electrons. Now later on we're going to learn about formal charges, and we'll realize that there is a better way of writing the Lewis structure for CO2. Okay, what about the next one? CH3+. So the first thing we're going to check is that we have the correct number of electrons. So we get 4 for the carbon, 3 times 1 for the hydrogens, and then we have to take 1 electron away to get the positive charge. So 4 plus 3 gives me 7, minus 1 leaves me with 6 electrons. So does what I have has what I've got there, got 6 electrons, 2, 4, 6. So it has a correct number of electrons, right? So the total number of valence electrons is not incorrect. The next thing is, does every atom have the correct number of electrons around it, right? Well, let's have a look at this. What have we got? We've got 2 for that hydrogen, 2 for that hydrogen, and 2 for that hydrogen. So that is good. But this carbon here, 2, 4, 6, it only has 6 electrons around it. But there's a little bit of a problem here, isn't it? Right? This is the best that you can do. Right? This is the best you can do because I only have 6 electrons. So how am I meant to have 8 valence electrons around the carbon? So this is a little bit kind of tricky here. This thing is electron deficient. It is a reasonable structure for for the formula that we're given. It is a reasonable structure, but some atoms also do have an octet exception. So I don't really quite know how to answer this. So I think that it would be very important to put an explanation here. So what I'm going to say is it is a reasonable structure, but also some atoms, and in particular the carbon in the middle there, don't have an octet. So that one's really, really, really tricky. Okay, what about the last one? All right, here we go. OF2. Oxygen group 6A gives me 6 electrons. I've got 2 fluorines. They're in group 7A. They each give me 7 valence electrons. 6 plus 14, 20 electrons. Do we have 20 electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So it has the correct number of valence electrons. Does every atom have an octet? 2, 4, 6, 8. The fluorine on the left has an octet. 2, 4, 6, 8. The fluorine on the right has an octet. What about the oxygen? 2, 4, 6, 8, 10, 12. Oxygen can't have 12 electrons around it. It's too many. Too many. So no, some atoms have the wrong number of electrons around them. The symbol of the problem atom is oxygen. So the only tricky one here is this CH3 plus 1, where it's kind of hard to decide, and I'd need you to put a little bit of text in there to explain your decision. All right. Draw the Lewis structure for the carbon pentafluoride molecule. It's going to have an expanded valence shell. So this can happen when we have a central atom that is period 3 or beyond. So we've got chlorine here and fluorine here, and chlorine is in period 3, so it can have more than 8 electrons around it. So let's add up our valence electrons. For ClF5, we're going to get 7 for the chlorine because it's in group 7A. And then we're going to get 5 times 7 for the fluorines. So 5 times 7 is 35 plus another 7. That's 32 valence electrons. So what atom goes in the middle? The one with the lower electronegativity. So electronegativity decreases that way. We also know that fluorine has the greatest electronegativity, right? So chlorine goes in the middle, and then 5 fluorines on the outside. There we go. So 42 minus 5 times 2, or minus 10, 32 electrons remaining after making those single bonds between the outer and the central atom. So we're going to complete the octet on all of the outer atoms, and in this case, how we're going to do that? Add 6 electrons, right? So we're going to add 6 times 5, or 30 electrons. So we'll take away 30 electrons, and that leaves 2 electrons remaining, and they have got to go on the chlorine. At this point, we check whether the central atom has an octet or not. 2, 4, 6, 8, 10, 12. It has way more than an octet, so what we're going to do, no need to make doubles or triple bonds. All right, so that gets me through one example of each of the objectives for this week, and I hope you found it helpful. And yeah, good luck with your test and everything that you've got coming up this week.